So in this video, I'm going to be explaining bisection in a little bit more of a mathematical sense. And I'm going to actually be running through our definition of the bisection algorithm. So in case you didn't remember from the last video, the bisection algorithm is basically this. You start out with some value of x, right? And you're going to check whether or not f of a times f of b is less than 0, then you're good to go and you can run the code. Otherwise, you're going to basically have the code fail and need to, reevaluate. And it'll display an error. Reevaluate your choice of A and B. But this will check if there's a sign change, and then you're just going to start the code. So you first set x to equal to a plus b over 2, and then while the absolute value of your function f of x is greater than your tolerance, then you'll basically keep running this section of code, and as long as it's greater than your tolerance, you'll basically improve it until finally this statement ends up being false because the absolute value of f of x is less than your tolerance, and then you have an x that is good enough by your y tolerance based standards. So while f of x is greater than tolerance, you're going to first see if the sign change is on the left half of the interval, which is defined as a to x. This if statement would be like further out than the while loop, like MATLAB would indent like this. And you would do if your f of a times f of x is less than 0, which this is the exact same sign change check, except instead of checking on the interval a to b, you're checking on the interval a to x. And then if that is true, then what you're going to do is you're going to set the value of b, which is your upper bound for the interval, is set to x. Otherwise, the value of a is set to the current value of x. I use these arrows instead of equals because it sort of better conveys the idea of assignment, which is what equals does in MATLAB. Then you press an end. Okay, so this will cut the interval in half by changing what a and b are. And then, now that you've changed what a and b are, you need to redefine what your midpoint x is. And so you would need to, of course, either way, set x to the midpoint again. Otherwise, if x never changes, then this value of x will exist forever, and that value of x never improves, right, if you never update it. So this is where you actually improve x. Then, once it reaches here, it'll evaluate whether or not x is good enough, and let's start the process all over again. Then if x is good enough, then you have this new x, and you can move on. You can move on with your life. And of course, the counterpart to actually running this code is just displaying an error. Some sort of error that you write. And then the end. So this is sort of the bisection algorithm, and this video is going to run through one run of the bisection algorithm, basically using the function y is equal to x squared. Y is equal to x squared minus 3, where the 0 is known to exist on the interval from 0 to 3.2. Okay? So I'm going to start out by seeing what f of a and f of b are, which is pretty easy. So if f of a times f of b, or let me just keep a tally of all my variables over here, which is going to be sort of a simulation of MATLAB's memory. So a is equal to 0 initially, b is equal to 3.2 initially, x is equal to x is not defined yet, remember, and then f is going to be some function you have somewhere, so x is equal to some undefined value, And yeah, that looks like all the variables we need to know at any one time. Oh yeah, and tall, I'm going to test for tall is equal to 0.1. Okay, so let's do this math. So let's first run through and see what this is. So f of a would just be a is 0, so 0 squared minus 3, so it'd be negative 3 times f of b, which is 3.2 squared minus 3, which is 7.24, is less than 0. So that ends up being equal to negative 21.72, less than 0, so that's true. So because this statement evaluates to true, it then will go run the block of code inside the if statement, which is from here to here. Okay, then we're going to set x equal to a plus b over 2. So x would then be equal to 3.2 plus 0 over 2, which is equal to 1.6. So x is now saved in memory space as 1.6. All right, so now we're going to do while absolute value of f of x is greater than tolerance. So we need to find absolute value of f of x. And absolute value of f of x would be absolute value of 1.6 squared minus 3. So it's the absolute value of negative 0.44, which is equal to 0.44, which is greater than 0.1, which is our tolerance. So we end up having this be false. What the heck?